I'll wait until maybe 1 or 2 minutes past the hour to get started, just to let a few more people join. Okay, I guess I'll get started. So hello, everyone. Welcome to Math 303, and this is Calculus 4. But in practice, this is going to be a course on ordinary differential equations. And my name is Astra Kolomatskaya. I should also write down my email address. My preferred email address for contact is firstname.lastname@gmail. Right. So this is the preferred contact address. And for things like office hours, I'll be doing them by appointment. So just send me an email anytime and we can schedule a mutually convenient time to meet, which means I'm essentially offering unlimited office hours. Now, a bit about me. What I study is something like higher dimensional logic. So I study about how can we talk about shapes inside of logic, where shapes are sort of a fundamental concept. And it's fundamentally different from a discrete kind of logic. And we can ask, for example, are two shapes the same as sort of primitives in the theory? And who I work with is Emily Reel at Johns Hopkins. Although, I mean, I'm a Stony Brook grad student. Now that area is about as far as you can get from differential equations, so I will be learning a lot from teaching this course as well. I actually never took a differential equations course during my undergrads, or an ordinary differential equations course, I'll clarify, because it wasn't required and I made a point of not doing so until my fourth year where I decided, you know what, I'm going to take one differential equations course. It's going to be a course on elliptic PDEs. And I assure you that in that course on elliptic PDEs, the one thing that we did not do was actually solve any differential equations. We did like horrible things that can't be unseen. And when I say can't be unseen, I mean, I've forgotten all of them by this point. But when I was in high school, I sat in on a differential equations course at the University of Toronto taught by Victor Ivry. And that was a good course. It was fun. Like I did the quizzes and exams. And I emailed him and he gave me his course materials. So this course will actually be very similar to the University of Toronto course that's usually offered. Now I'm going to start with the material by doing a review of integration, or at least half of it. It would be the entire lecture if I did all of integration. And that seemed a bit excessive. So I guess I'll do part 2 later. Before that, does anyone have any questions about the course structure? And also I should have emailed you the syllabus, and that is definitely one thing which is good to read. Okay, cool. So let's get started. And so we're going to start with a review of integration, part one. Right. So let's start off by recalling what chain rule says. And so does anyone want to tell me what the statement of chain rule is?
If we're taking the derivative of or wait, like in regards to derivatives, or
Well, what are we taking the derivative of? It's supposed to be a statement about taking in single variable calculus derivatives of functions, right?
yeah. So if you're taking derivative of a function inside a function, you take the derivative of the big function and then times it by with the little function side times the derivative of the little function.
Yes, exactly. I'd personally say inside and outside function, but a little function and big function work as well. So that's the rule. And the notation that I'm using right here is that this circle denotes composition. So in other words, this expression can also be written as, well, it sort of can't be written as f compose g of x is equal to f of x, f of g of x. But the thing is that I want to take the derivative of a function, and that function is the composite function. So I have to use this notation. But anyway, good. So correct, that's the statement of chain rule. And what we can do with chain rule is that we can integrate both sides. So as a consequence, we get that f of g of x, which is also the integral of the derivative of f and g of x. And when I say integral, I mean it's a indefinite integral of this expression. Well, what's that equal to? That's equal to the integral of f prime of g of x times g prime of x dx. And then sort of the constant would be inside of this integral. Now, what we're going to do is suppose that we have capital F prime is equal to little f. Then this rule becomes, in that notation, that's capital, well, if we're trying to integrate f of g of x times g prime of x, then that's capital F of g of x plus c, where capital F is obtained by integrating little f. And the way that we're going to denote this, and this is how you will use substitution in your assignment. I want it written in exactly this form, is if you have an integral f of g of x times g prime of x, then, well, I have the opportunity to switch colors. And I mean, it would be nice if you did that as well, but it's not necessary. I'm then going to say, introduce a new variable. Let's say that variable is u in this case. So I'm going to say, let u be g of x. And then below this, I'm going to write what du is. So this is supposed to be the derivative of u with respect to x, except for the fact that I bring the dx over. It's sort of an abuse of notation, but this is how we denote things. And that's going to be g prime of x dx. So in particular, with these substitutions, what this expression should be, and the green isn't part of the solution, I'll just write it here, is that this is the integral of f of u du. If you have that u is this and du is this, and if you just substitute these things in, then that expression becomes the integral of f of u du. So I put these angle brackets and I write these two items, and then I continue to say what this expression becomes. So with respect to that, that becomes the integral of f of u du. I guess I didn't have to write it in green because I was going to write it here anyway. And then suppose we've already evaluated that, and we know that that's f of u plus c. What we do then is we do one last step, which is substitute back in terms of u to get an expression in terms of x, because the starting expression is in terms of x. And so u is g of x. And then I usually like to just put square boxes at the end of my proofs. Sorry, at the end of my calculations. So this is notation that I really like and that I'm going to require you to use. And I'm just going to give a few examples of how we, so this is known as substitution. So let's say we're trying to integrate something like x2x over x squared plus 1 dx. So in this example, what substitution would I make?
Let u equal x squared plus 1.
Sorry, I didn't hear that.
Let u equal x squared plus 1.
Good. That was clear. And so what is du?
2x.
Yeah, and you also should write the dx. So in this case, the top, we have 2x dx, so that just becomes du. And here we have u. And the integral of 1 over u is what?
Natural log of u.
Yeah. And for logarithms, I don't like the notation ln. I actually write log. This is always the natural logarithm. And there's actually an interesting catch. To be fully general, it's the logarithm of the absolute value of u. Because you can see that log u and log minus u, they both have the same derivative by chain rule when dealing with the minus case. And now what we're going to do after we have this is we're going to substitute in for u. So we get logarithm of the absolute value of x squared plus 1 plus c. And that finishes up this example. So that was a pretty direct one-step substitution. And this expression was here, and it's literally a derivative over the function. So this substitution sort of is begging to be made. But there are some examples in which it's less clear. I'm going to give a slightly more interesting example right now where you have to think a bit before you get the right substitution. How about if we integrate x divided by x to the 4th plus 1? So what substitution should I make here?
Maybe you have u is equal to like x squared or something like that.
That's actually really smart. And that's exactly the substitution that we want. So if u is x squared, what is du equal?
2x dx.
Good. and you remember to say dx, so that's also good. And then with respect to these expressions, how can we write this integral in terms of u?
It would be like 1/2 of 1 over u squared plus 1.
Exactly. So here we have x dx. And if we bring the 2 out front, we get half du. I'll just bring the half outside of the integral. So x dx becomes half du. And then at the bottom, x to the 4th is u squared because u is x squared. So this is going to be u squared plus 1. And this integral right here, it's actually just solved by inspection because there is a standard function in your calculus A toolbox whose derivative is 1 over u squared plus 1. And which function is that?
Okay.
Exactly. And now finally, we substitute back. So in this case, the expression x squared as the thing that you're substituting doesn't appear directly as sort of a sub-expression of this. You have to realize that x to the 4th is x squared squared. So this is a bit of a more clever example. Now, the other thing that I want to emphasize in these examples is that what I'm doing is I'm writing the example like an analytical English essay. You can think of these expressions as being nouns and the equalities as being verbs. And so I'm chaining together sentences. I'm saying this is this. Why is this this? Because I'm making the substitution that I indicate here. This is this. Why? Because I'm applying some rules. And so, okay, I don't have to say that I'm applying the rule for how to integrate 1 over x. We know that. But the point is that it's a complete sentence. I don't just have expressions all over the place. They are connected by equalities. And this is something that I have to see when you submit your work. So you can't just have expressions. I'm looking for really high quality solutions that read like an essay. And so I'm trying to demonstrate how those would work. And yes, you do have to denote what your substitution is using this notation that I've introduced. Any questions about that? Okay. And now I'm going to do one very tricky example. Just to show you the main point here would be how you deal with a long example and how you write it. So what you should be learning here is how to present your solutions. And the integral is going to be the integral of 1 plus e to the x, the square root of that expression dx. So we're going to start with the substitution. What substitution would you suggest?
U substitution?
Well, yes, but what is u?
Should it be 1 plus e to the x in this example?
Sure, let's try that. So in which case, what is du?
E to the x dx.
Exactly. Now, the thing is that at the moment, there isn't sort of an e to the x dx in this expression. So one thing that I'm going to allow you to do is after you declare the substitution that you're going to make, you don't have to rewrite it in terms of u right away. You can sort of massage the expression first and then do or two later. So I'm going to take this expression, I'm going to rewrite it so that there's an e to the x dx. And how I'm going to do that is, well, I have this expression, the square root of 1 plus e to the x. Then I'm going to divide this by e to the x and multiply it by e to the x. One of my instructors once said that there are only 2 tricks in mathematics, and they are adding 0 and multiplying by 1. So here we have multiplied by 1 in a specific way, because e to the x over e to the x is 1. Now, the next thing that we're going to do is that the expression for u is 1 plus e to the x, right? And the denominator here has e to the x. So this isn't exactly ideal. We're going to take this and we're going to make this look like it has 1 plus e to the x. And how do I do that? What do I write here?
You just write -1 on the other side.
Exactly. Good. And now that I've sort of done these 2 steps of manipulation, I'm ready to rewrite this in terms of u. So if I try and rewrite this in terms of u, what do I get?
Square root u over u minus 1 du.
Good. Good. Now, sure, I have this expression. And what can I do with it? What should I attempt? Any suggestions?
Maybe try another u substitution.
Sure. So now I have to not use u because u is already in use. So I'm going to use a different variable. And I guess the next variable to use naturally is w. So what should I let w be in terms of u?
U minus 1.
Okay. Well, so let's see what happens if we try that. This isn't the best substitution to use. If we try that, we get that dw is du, right? And so all that does is it basically shifts the variables. What happens then is that we get, oh, by the way, I'm about to erase this. And so I should tell everyone that if anyone is currently making notes, then that's not necessary because I'm going to post everything that I write here at this file as a PDF onto the course website, which doesn't exist at the moment, but it will by Friday. And I can email this file out immediately after the lecture in any case. But anyway, going back here, so what happens is that, well, this is u. So I guess we to write it in terms of w, we'd say it's, well, u is w plus 1. And then the u minus 1 just becomes a w, dw, sure. But that doesn't like sort of give us a lot of progress. This sort of looks the same. And then if you try another substitution and try substituting v equals w plus 1, you get back to the original expression. So what's another thing that we can try?
Maybe since we like squares better than squares, we could try w equals square root u.
Yeah, good. That's good. And so I want the blue color. And so in this case, what is dw in terms of du?
Uh, 1/2 square root u du.
Yeah. And I'm going to write it like this. Good. And now I'm going to do the same thing that I did before, and that it's sort of not immediately obvious how I rewrite this in terms of w, so I'm going to massage it for a few steps. So I want to have a square root to root u outside. So I'll multiply top and bottom by square root u times 2. And so the two square root u's multiply to give u. Right? And at this stage, I'm actually ready to go. Because if we remember, if w is the square root of u, then what is u equal to?
W squared.
Good. And so here, I can take this expression and I have this dw here. And what does this become?
it becomes so it just becomes 2w squared over w squared minus 1 times dw.
Perfect, thanks. Okay, now notice in the work so far, I have been just doing an unbroken series of calculations of equalities. Now I have two choices. I can either pull something out of thin air, or I can actually do partial fractions directly. So this is a rational, actually no, before I say anything about partial fractions, I'm just going to mention that this expression can be rewritten. Notice that this is equal to 2 w squared minus 1. And then in order to be correct, what do I need to write here?
+2.
Good. So that's equal to 2w squared. I subtract the 2 here and I added 2 here, divided by w squared plus minus 1. And the reason that I'm doing this is because whenever you have a rational function, which is a ratio of two polynomials, and the degree of the numerator is greater than or equal to the degree of the denominator, then you can essentially do polynomial long division and just bring out a polynomial outside of the fraction and then have the degree here be strictly less than the degree here. And so this gives me a 2 outside of the integral. I mean, not outside the integral, outside of the fraction. Now, the expression, so now I'm going to break the string of equalities and I'm going to return to it later. So I'm not going to write an equal sign to sign here. I'm just going to think about the expression so first off, w squared minus 1. How can I factor this?
W minus 1 times w plus 1.
Good. And so what I'm going to do is I know about partial fractions. And so I know that any sort of ratio of polynomials where the degree of the numerator is less than the degree of the denominator can be written as a sum of rational functions where these are the denominators. So I'm going to consider an expression of the form a divided by w minus 1 plus b divided by w plus 1. And if I try and combine these, I get a times w plus 1 plus b times w minus 1 over w minus 1 times w plus 1.
So a could be 1 and b could be -1.
Yeah, so that's what ends up happening because this is going to equal to 2 over, well, I guess I can, the denominators are equal. So what we obtain as a result, and notice that what I'm going to do is there's a difference in math between equalities and implications. I've done this reasoning and then I'm going to say, because of this reasoning, I know something else. So I use an implication arrow. It's what I'm going to write here isn't equal to that. And so it would be really wrong to write an equal sign. And so I have that these two fractions are equal and they have equal denominators, so they have equal numerators. So I have that w times a plus b plus a minus b, I guess, is equal to 2. And that gives me two equations because I have to match the coefficients. So I get that a plus b is equal to 0. And I get that a minus b is equal to 2. And so to solve this, well, I have if a equals b, if a equals minus b, then I have that 2a is equal to 2. So that tells me that a is equal to 1, which tells me that b is equal to -1. Now, what I'm going to do is I've done this calculation here. And if I want to say what the conclusion is, it's that 2 over w squared minus 1 is equal to, let's see, the a term is on the w minus 1. So 1 over w minus 1 minus 1 over w plus 1. Okay, now what I'm going to do is I want to return to this calculation. Now there's a sort of trick for doing that, which is that I'm going to write equals to, and then I'm going to put a star here. So instead of rewriting the expression, I'm just going to assign it to the star. And then I'm going to go back here and I'm going to pull the star back here. And so that tells me that I'm continuing with the string of equalities, sort of with this as something that I did in the middle, right? So that's a good way to sort of break your reasoning and then return to your reasoning and make it clear that what you're doing is you're returning to that string of equalities. And then maybe I can even box this in. Maybe that looks a bit more clear even. And so now what I have is this expression right here, and we figured out how to write 2 over w squared minus 1. So we have that 2 here. And then we have 2w squared minus 1, which is 1 over w minus 1, minus 1 over w plus 1. And all of that is integrated with respect to dw. And now, basically, these are integrals that in calculus A, you're allowed to solve them by inspection. So let's just write what you get as a result. What's the integral of 2 with respect to dw?
2w.
Yep. Now for the next term.
The log of w minus 1.
Yeah. And I would like to write absolute value bars, although as we'll see later on, we're sort of going to drop the absolute value bars when we do differential equations. And then for the last term.
Log of w plus 1.
Yeah, and there was a minus sign here, so we should remember that. And then we should remember the constants, which I just squished in at the end. It's not good to squish things in that much, but sure. Now we can actually rewrite this. It's a difference of logarithms.
So you do.
And I personally like to keep my differences of logarithms into a single log. So what logarithm would that be?
W minus 1 over w plus 1.
Exactly. By the addition rule for logarithms. And then what I do is now I remember what my substitution was. Well, I had 2 substitutions. So w was square root u. So let's go back here and we're going to write this as 2 square root u plus logarithm of the absolute value of square root u minus 1 over square root u plus 1 plus c. And then we go back and we look at what our previous substitution was, and that was u is 1 plus e to the x. So this becomes 2 square root 1 plus e to the x plus the logarithm of the absolute value of the square root of 1 plus e to the x minus 1 divided by square root 1 plus e to the x plus 1 plus c. My wrist actually hurts a bit after writing all of that. Okay, so this was a very extended example. And we did substitution twice, and that's exactly what I had in my notes. Although you can also think of, instead of doing 2 substitutions in a row, you could have actually substituted u is equal to the square root of 1 plus e to the x all the way from the start. But I wasn't expecting people to suggest that. If someone had suggested that, I would have gone through it and then we would have only done 1 substitution. But in this way, we did 2 and the variable changed. And we had to remember that after we did the 2 substitutions, we had to undo both substitutions by substituting back in turn. And then we also had this quick review of partial fractions in the middle of it. So all of these were things that you should have seen in your course on integration. Although I'm reviewing them and you'll have a bunch of time to get comfortable with them again this semester. Any questions about that example? So can I put it all on one screen? Yes, I can put it all on one screen. No, not exactly. Okay, it looks very small now, but it is on one screen. So this was a pretty extended example. This is like a pretty challenging integral to do. You had to do a bunch of work. If you're sort of really comfortable with the techniques, then maybe it's a bit routine. But if you're not, then you have to practice at it for a while and maybe try a bunch of things, and maybe a bunch of things of those things wouldn't work. But that's what problem solving is. Okay, so this concludes the review of substitution, but we have one more thing to review, which is parts. So I started here with chain rule. So now I'm going to talk about product rule. So what does product rule say?
Isn't it if you're taking the derivative of 2 functions that are multiplied by each other,
Yep.
you add both the multiplication of the derivative of like fx and then the derivative of the other, if that makes sense, like the derivative of
Yep.
the first one.
To what?
To the other one, so then it would be fx times the derivative of gx.
Good, exactly. Right, so that's the rule. And so what we're going to do is we're going to integrate both sides again. And the integral of the left-hand side is easy because it's already a derivative. So f of x times g of x, that's just the integral of the derivative of f and g. And then if it's a dot, then it's multiplication. If it's a circle, then it's composition. So this just denotes multiplication. And so what that is that it's going to be an integral of this expression, but that's a sum. So I can split that up into 2 integrals. And then what I can do is I can rearrange this. And how I'm going to choose to rearrange it is that I'm going to sort of bring this thing over. I'm going to bring this over to this side and then swap the sides. So from this, I can conclude that the integral of f of x times g prime of x is equal to f of x times g of x minus the integral of f prime of x times g of x. And so there's a way that you can think about this rule intuitively. It's suppose that I have a product, an integral of a product of 2 things. Then what I can do is I can integrate one of the terms and differentiate the other term. So what I'm essentially doing is I'm bringing the derivative over from one term to the other. And what happens when you do that is you have the penalty of a minus sign. So you get a minus sign, but then you also have to add the product of the 2 expressions at their most integrated forms. And there's a notation for this. So the notation would be you'd have the integral of f of x times g prime of x dx. And now it's going to look pretty silly. But what I'm going to say is that f is equal to f of x. Usually f of x would be a more interesting expression. You wouldn't just be writing f equals f, you'd be writing like f equals x squared. And then I have the expression dg is equal to g prime of x dx. So basically what happens is that this expression right here, what it should be is integral of f dg, right? And then what chain rule says is that this is equal to fg minus the integral of g df. Okay, so once I've written this row, I've chosen which function I'm going to differentiate, and I've chosen which function I'm going to integrate. So if I differentiate f, I get that df is equal to f prime of x dx. And I get that g, the integral of this expression g prime of x, is equal to g of x, right? And so the new integral is going to be the product of these two expressions with a minus sign, and the cross term is going to be this diagonal right here. So this is equal to, I now should switch colors back to red. So f of x times g of x minus the integral of the product of this bottom row, f prime x gx dx. And then I go on from there. So the thing is that when I want to show that I'm using parts, I'll write f is some expression, dg is some expression, dx. Then I'll differentiate this and I'll integrate this. And then I'll write this next expression as this product of the diagonal times the integral of this bottom product with a minus sign. And the original integral should be this top product, the integral of this top product. Does that make sense? Any questions?
Can we use du and dv, like uv, du, and dv? Because that's the way I've always done
So
integration by parts.
the thing is that when I taught calculus B, I used u and v instead of f and g. But the problem is that sometimes you're doing a substitution, and then you've changed the variable to u. And so you end up writing something like u equals u squared. And the thing is that you're really not going to be practically using f and g as variables. So I actually think that for this course, I'm going to sort of keep the symbols f and g here fixed, because you run into some very weird things just by conventional letter uses if you use u and v. Does that make sense?
Yeah, that makes sense.
Cool. Any other questions? Okay, so let's do some examples. And how many do I have? I have 4 examples. Okay. With the last one combines the 2 techniques. So I guess this is one of the easiest examples ever of integration by parts. Let's say I have something like x e to the x dx. So basically, when you look at this, you ask yourself, okay, this is a product of 2 functions. Which function do I want to differentiate and which function do I want to integrate? So what function do I want to differentiate to make it simpler?
X.
Yeah, because if I differentiate x, I just get 1, and 1 is simpler than x, right? And so dg would be e to the x dx. And so you can see that the integral of x e to the x dx is the integral of the product of these 2 things, right? Okay, so then I'm going to differentiate x, and I'm going to write df is equal to what?
dx.
Exactly. And if I want to be absolutely clear, I can write 1 dx, although that's completely not necessary. You don't have to write the 1 there. Maybe it's just for some pedagogy. And then if I'm trying to integrate e to the x, what's the integral of e to the x?
E to the x.
Good. Okay, So I've set this up, and now I'm going to get first the diagonal term, right? So that's x e to the x. And then I'm going to get minus the integral of the bottom product. So that's just 1 times e to the x. So that's just the integral of e to the x. And what's that equal to?
Minus x e to the x minus e to the x plus some c.
Good. And then, yes, you have to remember the plus c. And then, I mean, I could factor the e to the x out. Okay, sure, not necessary exactly. Good, done. Okay, a slightly more interesting example. Let's integrate the logarithm of x. This is also going to be done by parts. So what am I going to differentiate and what am I going to integrate?
Log of x.
Maybe
So the suggestion was to differentiate the logarithm of u. But if I'm differentiating the logarithm of u, then what does dg equal to?
1 dx.
Yes. So we're implicitly getting a 1 here. And that's the trick to this example, because this doesn't look like it's a product of anything, but it's actually a product of the thing with 1. Everything's a product of itself with 1. So it would be wrong to integrate logarithm because that's what we're trying to do in the first place. So if I try to put logarithm here, then I'd be stuck because I'd be right back where I started. Whereas this is something that we know how to integrate pretty directly. So df is equal to what?
1 over u.
Yeah, du. So I'll write that as du over u. And then the integral of 1 is
X.
Yeah, and x is the right variable to use. And so, okay, then we get the cross term, which is x log. Sorry, there is, why are there u's? Why did there suddenly appear u's? Why did I? Okay, there should not be u's. I don't know where the u's came from. Log x. Df is dx over x. Okay, sorry about that. So x log x. Then minus the integral of the bottom, and look at this. This is actually pretty nice. We get x over x dx, so that's just 1, and the integral of 1 is
X.
good. And then we put the plus c, and we are done. Okay, now here's a really classic example. What happens if you're trying to integrate e to the x sine x? What will we differentiate and what will we integrate?
Does it matter?
It doesn't. Choose.
Let's do what's ex differentiate.
So we're going to differentiate e to the x, and we're going to integrate sine x dx. So df is
E to the x dx.
good. And now let's see if you remember the sign correctly on this. G is going to be what?
Minus.
Negative
Good.
cosine.
Yes, so it's minus. So the way that I remember it is that sort of sine is nice when you differentiate it, but also you don't have to think about it like that. You should also just think about it like this. So let's suppose that this is sine, right? What's the derivative here? So the derivative here is 1, right? So sine prime of 0 is equal to 1, and cosine of 0 is equal to 1. So the derivative of sine should be cosine, not negative cosine. But then when you're integrating sine, it's the other way around, because the antiderivative is, the derivative of cosine is negative sine. So the derivative of negative cosine is sine. If you completely forgotten it and you need to remember it, although this course will sort of, I guess there will be an oral exam, but there won't be any sort of timed exams. So you can look this up anytime as to what the derivative of cosine is in these notes or elsewhere, sure. And so what we get is the diagonal term, which is minus e to the x cosine x. And then minus the bottom product, but that becomes a plus because there's already a minus sign here. Okay, what are we going to do now?
Do it one more time.
Exactly. So let's do the same things. Where dg cos x dx. I don't like it when things get scrunched at the side of the board. I can just do move this over a bit so you can move a bit more space. Okay, yeah, so df is e to the x dx. I've already asked this several times. And now, okay, the sign is going to be the opposite that you had here. So if integrating sine gave you a negative sign, then integrating cos isn't going to give you a negative sign. So g is sine x. Okay, and so what happens is we do parts again. So we get minus e to the x cos x. And then we get the diagonal term, which is e to the x sine x. And then we get minus the bottom integral, which is e to the x sine x. And now what do we notice at this step? What's the trick?
Because we define something in terms of what the thing. So it's just like x equals 1 plus x.
So the key, yeah, like basically the key is that we started with this and we got it in terms of this, right? So what do I do with it? What do I do with this equation?
Don't you like put it over 2, like divided by
Yeah,
half?
well, I mean,
And
I
multiply by
take
half,
this thing right here and I bring it over to this side is what I do specifically, right?
Yeah.
So that gives me 2 times the integral of e to the x sine x is equal to e to the x, let's say sine x plus cos x. Right? Now, I don't have a plus c, and I'm going to have to introduce a plus c because I'm going to need that in the general integral. So what we get is that integral of e to the x sine x dx is equal to half e to the x sine x plus cos x. Not sine x plus cos x, sine x minus cos x. And then I should remember the plus c, and that finishes this calculation. Okay, so this is this trick occasionally comes up, and notice it would be very wrong to write an equality here because this expression is not equal to this expression. What I have is I have a sentence or a series of sentences saying this equals this, right? And I've written the reasons here. And what I do is that because I've made an assertion that this equals this, there's another assertion that follows from it. That assertion is that this equals this, but this does not equal this. This assertion is something that follows from this by rearranging this equation, right? So you have to be very careful, and I will absolutely yell at you on assignments if you use equal signs and implications incorrectly and interchange them, because they mean very different things mathematically, and you want good, clean, well-presented solutions. That's what I'm going for, right? And I'm going to do a final example, and then we are going to take a break. So the final example is going to be the integral of arctan. Okay, so what are we going to integrate and what are we going to differentiate? Well, we're certainly not going to integrate arctan because we don't know how to integrate arctan. That's what the problem is, right? So we're differentiating what?
Arctan.
Yeah.
It's like the same trick as the log curve.
Exactly. And so the same trick as before, dg is 1 dx. Okay, what's the derivative of arctan? I guess it came up before when we integrated it.
1 over 1. Oh, 1 over 1 plus x squared.
Exactly. And so, and then just the integral of 1 is x. Okay, so we get this cross term, x arctan x. And then we get this bottom term. So we get minus the integral of x dx over 1 plus x squared. And this is actually the first integral that we did today. What are we going to do?
Mu substitution.
Yep. So we're going to use both tricks in this example. And what is u going to be?
X squared.
Just x squared?
Or plus 1. Oh yeah, x squared.
That's much better because then the denominator just becomes x, and then the derivative of x squared plus 1 is 2x. So that handles the numerator, so we just get a logarithm. Whereas the other example, you get 1 plus u, and then it's not as nice, right? So you get 1 over x. Actually, you know what? You know what? Why not? Let's just do it like this instead. This also works. Then a du is equal to 2x dx. This also works. It really does, actually. Now I'm going to accept writing this. I'm going to write an expression that has both x and u inside of it. Some people might object to that, but you know what? It's fine from the standards that I'm going to set. If you didn't want to do this, you'd solve this integral separately and then use the equals to star trick to transfer the expression at the end. So if you're doing this, then you get 1/2. Then this becomes a du. And the 1 plus x squared becomes a u plus 1, right? And this is fine. This is fine. So what does that give me?
Minus 1/2 ln u plus 1.
Yep. And then I like to put the absolute value bars as well. Slightly more general. And then I substitute back. So yeah, both substitutions work equally well. Cool. Okay, so both tricks were combined. And so there is more to integration. There are trig integrals. I guess we only touched partial fractions a bit. And then trig integration is like an entire big subject, which occupies another hour's lecture. But cool, sure. So we got to substitution and parts, and we did a very quick recap of partial fractions. We are now actually going to talk about differential equations, but only after taking a 10-minute break. And so look, it's 59 minutes, very conveniently on the hour. We're going to resume at 7:10 p.m. Sounds good? I can also answer any questions before then. Okay, I will turn off my video and audio for the moment, and then I will go and make myself some coffee. which I will enjoy. Let's see. Okay. Everyone can hear, see me and the board, right? So we're good for video and audio and board feed, right? Someone confirm?
Yes.
Good. Okay, so let's, oh, there is chat. That probably is someone saying, yeah, okay, cool. Let us get started. So now we're actually going to talk about ordinary differential equations. Right. So in general, this is going to encapsulate most of the problems that we solve in the course. We're also going to consider systems of differential equations, and that's going to encapsulate the rest of the problems. But if we're not looking at a system, when we're just looking at a single differential equation, I can give you the general form of it. In general, a nth order ODE is an equation of the form so what it's going to be is it's going to be some function. And then in general, we're going to talk about x and some function y of x. So I guess I'll write it here. Here, y is some function of x. And so the equation that we're trying to solve for, and what we're trying to solve for is y, is that the equation can use x. It can also use the information of what y is. It can also use the information of what the derivative of y is, and all the way up to the nth order derivative of y. And so we're going to have some expression that's going to involve all of these symbols. So it can be an expression that has a derivative of y, it can have x in it, it can have the nth derivative of y, and we're going to say that that's equal to 0. And I mean, you can rearrange, but you can always bring everything over to one side and then get that it's equal to 0. And so to give an example, I just made up something off the top of my head. Let's say we have something like x squared, y squared, plus 2, y prime, sine x, plus e to the x is equal to 0. So what is this? This is some expression, right? It's made out of the functions that we know from calculus A, and in particular, it involves x, y, and y prime, right? And so this goes up to the first derivative, and so this would be a first order. ODE, right? Because it involves the first derivative, but not any higher derivatives. And the fact that I made this example from the top of my head, made it up from the top of my head, means that almost certainly it is impossible to express the solutions for this in terms of calc A functions. However, as we will discuss later in the course, we can prove that this equation does have solutions. But it's just the same as with integration. So for example, a very famous integral is the integral of the square root of sine x And this is known as the sine integral. And the reason it's known as the sine integral is because there's no way that you can write it in terms of elementary functions. But the integral does exist. There exists an antiderivative. Every single continuous function has an antiderivative. That's a theorem. But that doesn't guarantee that the derivative can be written in a nice way. And the situation is similar with differential equations. There will be some function y as a function of x that does satisfy this equation. You can prove that using some theorems. But that doesn't mean that you can write it down in a nicely expressible way. You can maybe describe that function as, well, the solution to this differential equation. That's a logical description of a function, isn't it? And so what happens is that actually, basically, this class is like a generalized class on integration. If you write down a random smorgasbord of functions combined together, it's probably not going to be something that you can integrate, but there are lots of nice cases in which you can integrate it. And so we're just going to learn a bunch of tricks as to how to integrate the special nice cases that actually do have closed forms. And that's basically going to be the whole semester. And like, is this important? Well, the important skill is to learn problem solving. And I think that's what I emphasize in my syllabus. So you're going to learn a bunch of techniques, and then you're going to have to chain those techniques, and then you're going to combine them and do interesting things. And what it's going to get you good at is having just a mental toolbox and being able to use that toolbox very deftly. And that's sort of like a mental agility and critical thinking skill. And that's good. And basically what calculus does, this class is called Calculus 4 after all, is it's problems of this form. It gives you a toolbox and it asks you to solve problems of this toolbox. Now, that may sound like I really don't care about differential equations. And to some extent, yes, my research is very far from differential equations, but I'm also actually going to tell you some things because differential equations are important in a bunch of areas of math as well, and engineering especially. But what really happens is that actually the interesting thing is solving differential equations numerically. So sure, the closed form might be impossible to write down in a clean way. However, if a solution does exist, you can find approximate numerical solutions, which are just going to be plots that represent the function that does satisfy the properties to some margin of error. And then if you do the calculation on the finer and finer scales, you can prove that that margin of error becomes very small. And so in practice, in the real world, in industry, if you're an engineer, then most of the time you'd solve differential equations numerically on a computer. And then you use those solutions and you pull them into other tools, and then you combine things, and then you get some numbers at the end, let's say. And maybe those numbers say like what thickness your bar has to be in order to support this bridge in order to ensure that it doesn't collapse, because you've just plotted a bunch of numerical data, and then a bunch of calculations and a bunch of complex PDE simulations, and then something. So yeah, in the real world, it's really applicable there. But this is sort of going to be the problem solving gauntlet version. But I am actually going to talk a bit like about numerics. It won't be something that I'm going to test you on. But it's going to be good to know as to like how computers are actually able to pull this out. And I haven't prepared that material yet, but I will by the end of the semester. But yeah, so I mean, if we think about it, what is integration? Integration is solving the problem y equals, solving the problem dy dx equals f of x, right? So if you know what the derivative of y is and it's f, then what is y? Y is going to be the indefinite integral of f, right? This is an example of a differential equation. But in general, we're going to have equations that aren't just y prime is some function of f. It's maybe going to involve y squared and the product of y and y prime. And then what do you do? Well, okay, maybe in this case, you don't do anything, you give it to a computer because this probably can't solve that. But in a bunch of nice cases, which are going to be artificially constructed, you actually can make progress. And that's what we're going to be doing all semester. So just to let you know. But okay. So let's talk about some classes of differential equations. And by the way, you can sort of classify differential equations. You can give names to them. Memorizing the names isn't that important. This isn't like a chemistry class. It's about solving problems. So I'm not going to ask you to like classify this collection of differential equations as, let's say, inhomogeneous constant coefficients second order ODEs. I'm just going to give you a very general type of problem. So this problem, dy dx is equal to f of x, is the problem of integration. But now let's generalize this a bit. Let's add in a twist. Generalize this one step. So let's see if anyone can tell me what a generalization is. Instead of telling you that the derivative is some function of x, what can you more generally consider? Well, okay, I'll tell you what the answer is. That's not necessarily a question that is very pointed. You can consider it as a function of both x and y. So we're going to write that dy dx is some expression involving both x and y. And so that's like a straightforward direct generalization of the problem of integrating, right? Okay, so this type of problem, it has a lot of geometric significance. So what we're going to imagine is that at every point in the plane, let's say A comma B, that's a general point in the plane. What I'm going to give you is a slope. And that slope is going to be f of A comma B, right? So for example, let's just say that this is my plane. And I'm going to draw some points on the plane. So let's say I consider these points on the plane. In general, this is going to happen at every single point in the plane, but I'm only going to draw a few of them. And so from a number, you get a slope. And dy dx, well, that's the derivative. That's the slope of something, right? So I can imagine sort of specifying, let's say, this slope here, this slope here, this slope here, maybe a really extreme slope here, and then something like this, and then something like this, and then something like that, and then something like maybe this, and then maybe it sort of looks vertical. Well, that looks not very continuous, but let's say I just do that. So I'm going to specify a slope at every point, right? And so the problem then is to find a curve such that, solution to this problem is a curve with the specified slope at every point. With the specified, well, instead of saying slope, it's with the specified tangent lines at every point. And in general, such description of a slope at every point, this type of problem involves giving what is called one of two things, either a direction field so that's the term that's used in like undergraduate differential equations courses, but there's also a term in pure mathematics that denotes this concept. And in pure mathematics, this would be called a one distribution. And the reason that there's a one preceding it is because you can also imagine not just working in two-dimensional space. Let's say we're working in three-dimensional space. And let's say that in specifying a line at every point, we specify a surface at every point. And then you can imagine sort of at every point you have a surface, and the solution would be some two-dimensional surface such that the specified tangent surfaces to every point are the specified tangent surfaces. And so in pure mathematics, in a subject called differential geometry, you consider problems like this. And there are theorems for when you can what is called integrate a distribution. And the main theorem is called the Frobenius integrability theorem. And we're actually going to get to some like very analogous statements to that theorem in this course. But then there's also theorems for existence of solutions to this problem. And one of the theorems is the Picard-Lindelof theorem, which is the main existence theorem for ODEs. And we'll also get to that. But anyway, so I'm going to give you an example of where this would come up in nature. So let's something like Q of t. Denotes the quantity of a radioactive substance at time t. And so how you think about radioactive substances is that they consist of a bunch of atoms, and you can think of these atoms as independent. And in any given instant of time, there's some chance that these atoms will decay. And the probability of an atom decaying is independent of the quantity of atoms that there are. Every single atom is has a given chance of decaying or not. And so what happens is the amount of atoms that you lose in a given instant of time is proportional to the total amount, right? Because if you have twice the amount, then those parts behave independently. So you're going to lose some atoms here and you're going to lose some atoms there. And they're going to be the same amounts of atoms that you lose in both parts as had it just been one part because they're independent. And so what you get is then that's the change of this quantity, the derivative with respect to t. Well, first off, it's decaying. So I'm going to put a minus sign. And then I'm going to put some coefficient, which represents sort of the probability of decaying in an instant, although in an instant, if you make it incredibly small, the probability is 0. But it's a coefficient that denotes this. And you can calculate it in various ways. For example, if you know the half-life, then using logarithms, you can tell you what this number is. And I'm just going to denote it for Greek alpha. And so it's proportional via a coefficient of minus alpha to the quantity of radioactive substance that there is at time t. And then let's say for some alpha between 0 and 1. Right? Does that make sense as equation? And why that would happen if you have a radioactive substance? So if we think about the problem of just regular integration with this equation right here. In this equation, the slopes that you can give, they depend only on x, which would mean that for a given x value, all of these slopes would have to be the same, right? But what happens in this equation is that there's actually no dependence on t directly. There's a dependence on q of t. So if you change what q of t is, so if you change the y value, it's actually going to change. And so what I'm going to do is I'm actually going to go to a programming language that I have here called brackets. And what I'm going to do is actually I'm going to stop. You know what? I'm going to not plot this. I'm just going to ignore that picture right now. And so what I'm going to do is that every point I'm going to specify a vector. Now a vector has both a length and a direction. And so what I'm going to do is normalize it. Which means I'm just going to make all of the lengths be the same because we only have a direction, not a length. Now, if as a vector, I give the rise and the run. And so if I want to specify it's to be have a certain slope, I'm just going to make the run be 1, right? And then I'm going to make the rise be the derivative. And in our example, let's say it's in the coefficient alpha is 1/2. So I'm going to multiply 1y by 0.5. And then I'm going to take minus that. And then I'm just going to consider the vector 1 minus half y. So that has a run of 1 and then a rise of minus half y, giving it a slope of minus half y. And then I could multiply both of these by any other number. I'm just normalizing it. And so what I'm going to do is it's going to sample a bunch of points and it's going to give you these direction lines and it's going to plot it. And so if I do that and I run this, you can see that I get a plot here. So let's look at 0. At 0, and unfortunately, can I make this bigger? I don't think I can make it bigger. There are some commands that I can run maybe inside of here as to what size I actually showed up. But anyway, so at 0, y equals 0 along this line, the slope is going to be 0 because we have half times 0, right? But then as y becomes bigger, these slopes are going to get bigger. And the slopes actually don't depend on x because this formula doesn't involve x in any way, does it? But involves y. So you can see that if I go along on an x, all of these directions are the same. But if I increase along y from 0, it starts off at 0 and then it just keeps on getting steeper and steeper. So what happens is if you start off somewhere big, then you have a lot of material to get rid of. And so the amount of material that you're going to get rid of in an instant of time is going to be bigger than if you had less material to start with, right? And so what would an equation, what would a solution be? You know what? I'm going to just copy this image and I'm going to see if I can paste it inside of here so that I can draw on it. So let's see if this works. I have no idea if this is going to work. So what if I just paste? Nothing, I think, nothing, sad. Okay, but so I can show you this visually. So what a solution would look like is it would be some curve. So that the slope of the curve, the tangent line to the curve at every point was the specified thing. And it's going to decay. And you've probably seen in something like Calculus B or Calculus C, or Calculus 2, if you took that sequence, that you sort of get exponential decay. Because if you have radioactive material, it decays exponentially in quantity. And so you'd get an exponential curve like this, decaying eventually to 0. And you can sort of see from this picture what that curve is going to look like. Because if you start here, well, how do I start drawing the curve? Well, here's a point and I know what the slope is. Then I move a bit and I know what the slope is. Then I move a bit and then I know what the slope is. And then I just do it tiny increments at a time. And then I get something that approximates the correct curve and it's totally almost smooth. And then if you make the amount that you move smaller and smaller, it's going to become more numerically exact. So I can even write a program and show it to you either next time or on Monday for how I'd actually draw curves on this. So I'm going to write a solver. And it's actually going to plot a curve on this plot, and that's going to be cool. And maybe I won't even have to write a solver. Maybe this package includes it. Any questions about that? Right.
I have a
so
question.
yeah.
So you started from like the top of the graph and like it made an exponential curve. But what if you started like from the bottom of the graph? Like would it just be, you know, like around -1?
Yeah. So that's an interesting question. And sort of negative starting values sort of don't correspond to reality, because what does it mean to have a negative amount? But suppose that you can have a negative amount of material, then it would decay to become less negative over time. So you can see that there's actually a symmetry in this plot of reflection along the axis y equals 0, right?
Yeah.
And so if I have an equation that starts somewhere from the top, then it's going to decay like this. And if it starts at the bottom, then you can just imagine mirror reflecting it to the top and getting the same sort of trajectory. So it's going to be a trajectory that's sort of the amount of material increases with time, but the amount of negative material decreases with time as well, approaching 0.
Oh, okay. Thank you.
No worries. Good question. Right, so this is this general class of problems. If you have a problem of this form, the interpretation is that it's going to be a specification of a direction field. And the question is, how do I integrate that distribution? Or in other words, how do I find curves whose tangent lines at every point exactly match the slope that you're specifying? Now, in general, there is no numeric solution to this problem. That you can write things for which, there are always numerical solutions. You can prove an existence theorem. Assuming some conditions, specifically, it has to be locally Lindelof. And I'll explain what that means later in very sparse detail because it's not important. But if you're asking about an analytic solution in terms of functions that you're familiar with, you won't always be able to solve this equation. But in some classes you will. And so I'm going to give first an example of the simplest possible class in which you're able to solve this equation, and that is known as the class of separable differential equations. And so how separable differential equations work, these are equations of the form dy dx is a product of functions where one function only depends on x and the other function only depends on y. So to give an example, y prime is equal to x squared y squared works, right? Because that's a function of x and a function of y. But y prime is equal to sine x plus y, or even y prime is equal to x plus y, are not of this form. Right? Now the question is, so let's suppose you have an equation that looks like this. How do I solve it? Well, this is where we're going to leave rigor completely aside. We're going to focus on problem solving strategies, and we're going to focus on how you present those problem solving strategies. The rigor is justified by this process works in the sense that if you then try and look at what dy dx is, you get a solution. So you can verify post hoc that you have a solution. But let's just replace g with 1 over g, so that the equation of this of the form instead of writing it like this, I'm going to write it like this. This is sort of the more standard way of writing it. F of x divided by g of x. So suppose this is where we're starting from. And ignoring dividing by 0, this class of equations is just as general as this class of equations. And again, we're throwing rigor out the door, so we are not going to ask ourselves about that divided by 0 case. And then what do you do? Well, it's actually the, this is g of y. G is a function of y. What, does anyone have a suggestion as to what to do?
Cross multiply.
Exactly. Make it cross multiply, then you get one side in terms of x and the other side in terms of y. Now, does it make sense to pull up apart a derivative? Well, why not? Why not? So we're going to then write that g of y dy is equal to f of x dx. And then we're going to integrate both sides. And so the general solution is the integral of, sorry, there should be an f here. Integral of f of x dx minus the integral of g of y dy is equal to c. So this is going to be some expression involving x and y, and it's not necessarily going to be isolated in terms of y. So you're not writing y as a function of x. Maybe your expression is something like x squared plus y squared is equal to 1, then that traces out a circle, right? But what it does is it defines a curve. And maybe you can solve for this curve as y as a function of x, and that's what we prefer to have in our solutions. Sometimes you can't do it perfectly because for the circle, it's sort of not a function. It doesn't satisfy the, it's called vertical. Yes, that type of line is a vertical line. It doesn't pass the vertical line test because there are two outputs for this input. So sometimes you'll get equations like this, and then they sort of trace out curves. But if those curves exactly match the specified tangents at every point, then you're happy. Right. So let's consider an example. Let's consider the example that we saw before. Dy dx is equal to some multiple of y. And for simplicity, I'm just going to assume that that multiple is 1. So dy dx is equal to y. So then what I do is I say that this implies, and then I separate the sides. This is why it's called a separable differential equation, because I isolate the part that has x on one side of the equation and the part that has y on the other side of the equation. So then I get that y dy is equal to dx, and then I integrate both sides. And then I evaluate both integrals. So what's the integral of y?
X. Oh, wait.
No, it's with respect to y. So consider y as a variable in this case.
Would it be dy dx?
Well, it's going to be some function of y.
Y squared over
Half
2.
y squared.
Yes, and I heard someone say the 1/2. So it's 1/2 y squared, right? Because what's the derivative of y squared with respect to y, not with respect to x? Well, you bring the 2 down, and so you get y, right? And then the integral of 1 with respect to dx is?
X.
Yep. Sorry, we made a big mistake. If I bring the y, it goes below the dx, right? It should be a logarithm after all. It shouldn't be a polynomial. What we actually have is dy over y is equal to dx. So the integral of dy over y is equal to the integral of dx. Okay, so the integral of 1 over y is?
Natural logarithm.
Yep, and then I'm going to put an absolute value. And what happens is I want to get rid of this logarithm. So I'm going to take both sides of this equation and use them as the exponents of an exponential. So the absolute value of y is one way of writing e to the log of the absolute value of y, because log and e are and the exponential are inverse functions. And so this is going to equal to e to the x plus c, which I can write as e to the c times e to the x. And then in absolute value, I can get rid of it by writing plus or minus e to the c, e to the x. Now, if you think about what e to the c looks like, then the graph of the exponential looks like this. And so the range is all strictly positive real numbers, right? But then there's a plus or minus, so it also includes all strictly negative real numbers. But then you ask yourself, does the solution, sorry, I should not have absolute value bars there if I did this. Does the solution y equals 0 make sense? And yeah, so if you just have y equals 0, the derivative is 0, right? So that works as well. So we're actually missing a solution. So more generally, y is equal to c e to the x, because this only represents non-zero real numbers, whereas this represents all real numbers. And it turns out that we somehow missed a solution when we were doing this. So how do we account for that? Well, so what we're going to do is it's going to be a shortcut. And again, we're going to take rigor completely out of the window when we do this shortcuts. This is how you're actually going to solve this problem for the rest of the course. So we're going to start off with the equation dy over y is equal to dx. Then we're going to integrate both sides. And then we're going to now forget about the fact that the integral has more generally absolute value signs. We're going to get rid of the absolute value signs. So we're just going to write log of y. I don't even have to write parentheses, I guess. I guess I like writing parentheses even when it's a single argument. And what that is going to equal to is it's going to equal x, and then I'm going to have a constant. Now the constant is going to be the logarithm of c, where c can also be a negative number, and 0, where in particular, if c is a negative number, the logarithm is not defined. But again, rigor out the door. We're just going to write this and see what happens. So I'm going to make my constant be of the form log c. And so then what happens is when I exponentiate, I get y is equal to c e to the x, right? And so that represents the fully general solution. We got all of the solutions except for this equals 0 from before. But if we actually just make the coefficient log c, then we directly get all of the solutions. So this looks like a more expedient path. So sometimes I'm just going to make my constant be some certain function of c and hope that that just makes the answer nicer. Does that make sense? Well, it should only make half an amount of sense, but that's the most sense that we're going to get in this case. It works. So sometimes we're going to make the constants be an arbitrary function of c, so long as it makes things work out in the end. And then you're sort of going to see from the example what type of function of c that you actually want. And so this is how you do it for the rest of the class. You don't do it this way, you do it this way. Okay, let's do our next example. Any questions about this, by the way? So let's consider something like dy dx. And let's do something interesting. Let's say that it's y over x. And let's just actually go back to Racket and see what this looks like. So if we consider y over x as a slope, that can also be expressed as the ratio of y divided by x. So sort of the rise is y and the run is x. So I'm going to sort of have a vector where the rise is y and the run is x. And then I'm going to plot this between 0 and 4. sorry, I want the run to be X and the rise to be Y. That would not make sense for the solution that we're looking for. Oh, look at this. Look at this. Okay, so looking at this plot, what does it look like the solutions are going to be? You sort of can see it from here.
Exponential.
Well, actually look at it. If it's 0, then it's always going to be 0, right? But let's say it's on this slope right here. Then look, that slope leads you to this point, 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 leads you to this point. So it looks like the 45-degree line is represented, right? Through 0.
So all lines about 0.
Yeah, so lines passing through 0, right? You can sort of see from this plot that if you can either have a perfectly horizontal line at 0 or a perfectly vertical line at 0, or the 45-degree line, or a line of any other slope. So from this picture, it looks like the answer should be lines of a given slope passing through the point 0, 0 for the origin, right? So bam, look, we've just solved the differential equation without actually doing any math and just looking at a picture, but let's actually do a calculation and show that that's what you get. I'm going to leave this up for a couple of seconds and take a sip of coffee.
Oh, it's just like m equals y over x and then mx equals y.
Right, because yeah, that's also another way to see it. I should have actually said that. Basically, the slope is x over y, and x over y is the rise and the run. And so if that's constant, then that works as well. So you can work backwards and see that that's actually is going to be a solution. Because if your run is x, your rise will, well, okay, if you have a constant ratio, then it's going to remain the same along this line, right? The rise over the run is the same along a line of a given slope through 0, and that rise over the run, that ratio is going to be that slope. Okay, let's go here and let's solve it. So what we're going to do is we're going to separate it. So we're going to write, again, this implies arrow because it's not equal. We're doing something from the equation. We're saying that this equation implies another equation. And that equation is going to be dy over y is equal to dx over x. And so we already integrated dy over y before. So we get the logarithm. And again, we're not putting absolute values now because we're going to do the constant trick, and that's sort of going to take care of all of the possibilities. Log y is equal to logarithm of x. And then what should I make the constant be?
Guess log c.
So that looks good because we have logarithms everywhere. And then we can actually rewrite log x plus log c as well.
Log xc.
Yeah. Cx looks a bit nicer from things because I like to have the number in front of the x, but sure, xc, cx, same thing. And so then I'm going to exponentiate both sides. So I have log y equals log cs, log cx. And by exponentiating, I get that y is equal to e to the log y. You don't actually have to write these middle steps. I'm fine with you just writing y equals cx. But I'm going to write it this time. But you don't have to. You could just write y equals cx. And so, bam, we get to the solution that the lines are exactly lines for the origin because there's no plus a, it's just y equals cx. So they're lines for the origin of a fixed slope. By the way, let's just do another interesting example. What about the example dy? And I actually don't have this in my notes, but now that I think about it, I should. Is equal to negative x divided by y. Right? So By the way, can anyone tell me what this is? Actually, no, it's not going to be fun if someone knows what this is. Let's just plot it and see what happens. So what happens is we're actually going to flip these two. And by the way, let's make the scale be from -4. -4 to 4 and 4, 4. And so we're going to swap X and Y, and we're going to make one of these negative. So what does it look like the solutions are going to be?
Circles about the origin.
Yeah, circles around the origin of a fixed radius, right? So what the constant is going to parameterize is essentially the radius. But you can see from this picture that, like, obviously it's going to be a circle, right? And sort of that makes sense because if you think about it,
Is the line perpendicular, like drawing from the origin to the point on the circle is a radius, which is the line we had before, which was y over x, but now it's the perpendicular, so it's at minus x.
yeah, exactly. So if this is the point xy, what line is perpendicular? Because the tangent line to the circle is perpendicular to this. And so I can draw that here in like bolder blue. So the slope, I guess this is a very hard to see color. I guess I'll write it in here. The slope of this line is going to be the reciprocal of, so it's -y over x. That's exactly the slope. So that's exactly how you see it. If you just think of a point here and you think of what's the slope, what's the line that's perpendicular to this line? Oh no, rather, what is the slope of this line? The slope of this line is the rise over the run. So the slope of this line is m is equal to, sorry, y over x. And here, this the perpendicular line, we know from sort of high school, is that if you have a line of a certain slope, the perpendicular line has slope negative the reciprocal of that slope. So the slope here is going to be -x over y. And so because we're taking the perpendicular line to the line from the origin, that's why you get a radial direction, and that's why you're going to get circles. And so we can actually verify this. We can bring this over, and so we get, I should write, I like to write the implications. Y dy is equal to -x dx, right? And so we integrate both sides. And this is a polynomial, so it's great. What's the integral of y?
Y squared over 2.
Yep. And then similarly here, -½ x squared. And now the constants. What's the nicest expression that we can use for the constants?
I guess 2c.
Well, 1/2, so that the halves we get rid of all the halves, right? And so let's write c. Sure. In that case, we get that y squared plus x squared is equal to c, right? Now, notice that, by the way, that this equation has no solutions when c is negative. Because squares are always greater than or equal to 0, because if you square a negative number, you get something that's greater than or equal to 0. So in fact, we could have made the constant c squared, or we could have made the constant r squared. And we're not losing solutions in this case. We're sort of running a risky game because maybe if you just randomly square a constant, you lose solutions. But in this case, you're not losing solutions. So perhaps the nicest coefficient constant that you could possibly use is ½ r squared, because then this represents the circle in sort of the circle of radius r, right? Okay, cool.
I just have a
That's
question.
a fun example. Yep.
Regarding why did we do a ½ r squared and not just say r squared?
Oh, Because if I didn't have the half here, then I'd multiply everything by 2 in order to get rid of these 1/2, right?
Okay.
And then I'd get 2r squared.
But
And
since
that's
it's
a
a
less
constant-
nice expression than if I had r squared.
Okay.
So the answer 2r squared is also correct because r is an arbitrary number.
All right. Okay. That was my understanding. Okay. Thank you.
Right. Any other questions? Okay, yeah, that was a fun example because we just plotted it and then we saw it exactly, right? So that's cool. Okay, the next example that I have on paper. And honestly, the expression isn't even that nice. Yeah, so for these examples, if we plot them, it's not going to be obvious what the thing is. Let's just do something like y dy over dx. So I guess we're just doing this example for the sake of doing another example, is equal to y squared plus 1 times x, right? So we are going to separate this. And so we get y over y squared plus 1 dy is equal to x dx. And then we've already done this integral before. So you should actually do this integral in full on your homework. But I'm just going to copy and paste the integral because we've seen it already. So what's going to happen is we're going to make this substitution y squared plus 1, and then we're going to get a constant of half. And so it's going to be half logarithm of y squared plus 1. Because we've literally done this integral before above, is equal to half x squared dx. Sorry, no dx, just a half x squared. And then so we have a logarithm. And at this point, you're just going to guess what the form of the constant is going to be. We're sort of going to exponentiate this to get y on its own. But there's also a factor of 1/2 everywhere. So let's just get rid of that factor of 1/2 by putting a half in front of it and then putting log c. Does that make sense? So the half is just to not have a factor of a 1/2, not have a factor of 2 floating in front of my c. And then there's a logarithm here, and we're going to want to isolate for y, so we're going to exponentiate it. So let's make the constant of the form log c. Cool. So now we're going to exponentiate both sides. And this time, I'm not actually going to have to write e to the log y. You're allowed to just write, we multiply everything by 2, and then we exponentiate. So we get y squared plus 1 is equal to, well, log c becomes a multiplicative factor of c, e to the x squared, right? Then, as a result, y is equal to plus or minus the square root. You're also allowed to do these steps, several steps at a time, because sort of it's just direct. It's clear how this line follows from that line. So long as you're not actually skipping any substantial steps between them, you can go between these two. So c e to the x squared minus 1. And then when you take the square roots, remember that you have to put a plus or minus sign in front of it, right? So if we actually look at an equation like this, it's an equation of the form dy dx. Let's see if we can see anything from the plots. I'm not sure if we'll actually be able to see it in geometric significance. So it's going to be a ratio where, let's say, the run is this and the run is y and the rise is y squared plus 1 times x. So the run is y and the rise is, I'm going to consider y squared, so times y. And this is sort of this is an prefix language. So to get y times y, I write times y. And then we're going to add that to 1. And then we're going to multiply that by x. And I think that's that. Oh, I see. There's a superfluous set of parentheses outside of it, of course. So in rackets, basically parentheses denotes sometimes actually evaluation of functions. So if you sort of put a number and then put parentheses around it, it tries to evaluate the function as the number as a function. But so this is sort of a weird plot. Let's look at it. So if you start here, for example, you'd sort of have a parabolic trajectory like this, but it's not actually a parabola. And then sort of if you're here, then what does it look like? It looks like you're going into here and then it does like this. So if you're here, it actually does something like this. Can you see how I'm tracing my mouse out? If you're here, it does something like this. But if you're here, then it does something like this. So there's a point at which it starts, if you're here, it goes into this quadrant, but if you're here, it goes into this quadrant, right? And then if you're here, it would be like this. It would sort of move in here and then move out here. But if you're here, then it's enough to get captured and brought over onto this side. So I guess there is some interesting stuff that we can learn from here. And then at 0, it's undefined here, because in general, we're going to be dividing by this expression, although it's sort of y squared. So actually, no, this expression when x is 0 is the bad case. So at x equals 0, okay, well, sure, stop. It's only a problem if both of these coefficients are 0, and that only happens at 0, 0. So there might be some perfectly vertical lines, but the only point at which there's no line is 0, 0. Okay, sorry, that was a bit of a word jumble, but now that we actually got the differential equation, we can see what the solutions look like just by looking at the plots, and that's like an important point to learn here, right? Any questions about this example? Okay. And sort of, you can sort of imagine that if you had the solutions that we were looking at before that went, didn't transport you across here, but went like here, those solutions wouldn't be a function because they wouldn't pass the vertical line test. So that's why you need the plus or minus to get these solutions most generally. Now, here's an interesting example. Let's say we have something like dy dx is equal to 1 plus y squared divided by 1 plus x squared, right? So when we separate this, we're going to get dy divided by 1 plus y squared is equal to dx divided by 1 plus x squared. And then when we integrate this, we're going to get what function?
Arctan y.
Exactly. Sorry, that is a very bad y. That y looks like an x. Sometimes my y's look like x's. And so we get arctan y is equal to arctan x. And now let's do the high-brained thing. What's the constant going to be? What function am I going to take of c?
Is there maybe just arctan? Well, that's
Yes. Let's do arctan C. Why not? And so what happens is if we want to get this expression in terms of y, we take tan of both sides, right? Because tan is an inverse function to arctan. So as a result, by taking tan of both sides, and I'm going to write it here explicitly, y is equal to tan of arctan of y, which is equal to tan of arctan of x plus arctan of c. And so what happens is that there is a formula. So I'm going to write equals to star, and then I'm going to remind you about what the formula is. So you do not have to memorize this formula. And later in the class, we'll talk about complex numbers. And so there's actually a way to derive all of the trig addition formulas using complex numbers. And the way that I remember the formulas is I basically rederive them every time of complex numbers. But I'll just tell you what the tan addition formula is. So the tangent of a sum of two angles alpha and beta is the tan of alpha plus the tan. Sorry?
Oh, never mind. Sorry.
Plus 1. And then is it plus or minus? It's minus tan alpha, tan beta. Of course it's minus. Because I can sort of drive it in my head. And so when we take tan alpha and beta, this is why we used arctan C, because we're going to take tan of these angles. And so the arctans are going to go away, right? So this is why we wanted to write the constant as arctan C. So going back here, putting in a star to return to this calculation, what that is it's x plus c divided by 1 minus xc, right? Now, honestly, I don't know what this function looks like. Okay, I can plot it, sure. But let's just take a look at what this function looks like. So the run is 1 minus, let's set c equal to, actually, no, we go to the differential equation. So the run is 1 plus x squared, the rise is 1 plus y squared. So we're going to do the sum of 1. Then what do we want the run to be? Sorry, the run to be. The run is, I'm just looking at the paper, 1 plus x squared. And then the rise is the product of y with y. Cool. So that's that ratio that I had. And then let's just see what it looks like. Okay, that's interesting. So look at this. The 45-degree line appears to be present, right? So the 45-degree line is a solution. And then if you're here, you do like this, you do like this. And then if you're here, you do like this. So I think what this actually is, it's a hyperbola. So if you're here, you do like this. And so is there a symmetry? There isn't a symmetry around. Are there any symmetries? Okay, the symmetry is around the 45-degree line, right? And then there's, I guess, another symmetry here if you ignore the direction of the arrow. If you think only of the slope and not the fact that the sign is there. So there are 2 lines of symmetry here. And then the solutions look like hyperbolas, right? So we can see that from this plot. And then what we've just done is we've actually just given those level curves an equation. Okay, now it's actually 8:15. So I'm going to do Do we want to break? Let's do a break now. Let's do a 5-minute break. So resume at 8:20. Okay, see you in 5 minutes. Cool. Okay. Right. And so this example is going to be an example in population dynamics. Also, my headphones are weird. Why? Okay, no, whatever. So here's a population dynamics example. And so we're going to think of sort of this as the number of rabbits that we have. So let's say x of t is the rabbit represents the rabbit population at time t. Now, technically, this can be a number. So what does it mean to have a fractional number of rabbits? Well, it's an approximation of nature. So forget that there are fractional rabbits. The number of rabbits in an ecosystem at time t. Now, how this is going to work is that if there are just a very small number of rabbits, then it's going to look like the amount of rabbits are going to grow exponentially, because that's how rabbits naturally populate themselves, right? But the problem is that let's imagine sort of any species grows exponentially. Well, at a certain point in time, there's only a finite amount of space on Earth, although that's not going to be the constraint. There's only a certain amount of resources that the rabbits can access, and then they're going to start competing with each other, and then they're going to have fewer resources per individual. So at some point, the resource is going to be a problem. And so the population is going to be capped at a certain number, and that cap is going to be known as the carrying capacity of the population. And how this is going to work is that we're going to get that dx dt. You know what? Let's call it r. X is sort of a weird letter to use as the dependent variable. So dr dt, it's going to be some multiple of x. So if we just, sorry, of t. No, not of t. Time doesn't matter. It doesn't matter what time you're in. The only thing that matters is how many rabbits you have at a given instant, right? So kr. If I had kr, then we saw this example before, it would just be exponential growth, right? But what I'm going to do is I'm going to multiply this by c minus r. Maybe c is a bad letter to use because we're going to introduce that in the differential equation. So let's call this gamma minus r. And so if you think about this as a function of r, this is going to be some parabola with roots at r and gamma. And let's say that gamma is greater than 0. So we're going to have 0 be here, and then let's say gamma be here. And so what happens is if you're between 0 and gamma, you're in the positive part of the parabola, right? So that means that you're going to be getting more rabbits, right? So if your r is between 0 and gamma, that means that rabbits are being born and the rabbit population is increasing. But as you reach the carrying capacity, the growth rate of the population goes to 0. And if you're over the carrying capacity, the problem is you have too many rabbits and not enough resources. And so the population is actually going to go down because the slope is going to be negative. And then sort of if there are negative rabbits, then it's going to go up. But that's sort of fictional, right? And so what this example represents is something like this. Let's, by the way, consider on the plot carrying capacity of, I guess, 2. And let's look at what that looks like. So it's the run is going to be 1 and the rise is going to be r times 2 minus r. So it's y that matters, not x, because the time is immaterial. It doesn't matter what time it is. And so maybe I can, okay, I'm going to plot it like this. This is y, because we're using x and y as the variables here. Okay, so look at this. I'm just going to try and change this 4 to a 0 so that we ignore negative values, and I hope that I got the right one. I got the wrong one. This should discard the values below y equals 0. Yeah, so here is the line y equals 0. Notice that if there are 0 rabbits, then the population isn't going to grow. If your species is extinct, you're not going to suddenly start getting members of the species, right? But then let's say you have a small population relative to 2. The growth is going to look like it's exponential, but then eventually the carrying capacity is going to take over, and then it's going to look at like it's exponential in the other direction. And then it's sort of going to flatten out at the carrying capacity. So if you're here, it looks like this, right? And if you're here, then it looks like this, right? So eventually, if you start at 0, you have nothing. But if you start anywhere else, you're going to sort of converge asymptotically to the carrying capacity, which is 2 in this example. Does that make sense? And then sort of by changing 1 to some constant, so we have the value k. So let's see what happens if we change this 1 to a 2. Then it's going to sort of make the speed at which you get there slower. So right now, it's going to be a longer ride. So this number here determines how long it is before you get close to the carrying capacity. And so this is a standard example in population dynamics, and it's sort of an equation that's pretty easy to solve. And it represents this example where you have exponential growth here, and then you have exponentially slow growth here because you have the carrying capacity, and sort of you pass between one exponential mode to another exponential mode. Does that make sense? So let's solve the equation. So what we're going to do is, and interesting stuff is going to happen when we do this. Well, we're going to separate. So we get dr divided by r times gamma minus r. I'm going to make the page a bit bigger. Okay, equals to k dt. And we're going to integrate this. So I guess I can just write the integrals here. And you know what? I'm just going to choose to rearrange this equation, actually. What's the integral of k dt with respect to t?
KT.
Exactly. So kt is equal to the integral of dr divided by r times gamma minus r. Now, look, this is a rational function, right? It's a ratio of 2 polynomials. There's a polynomial at the bottom, and we factored it. So what are we going to do?
Like with the a over r and b over gamma minus r.
Exactly, and that's called partial fractions, right? The technique. So how you set it up, and you know what? I'm just going to do it in a different color. You know what? I'm going to put a box around it later. Same color. So we're going to consider the quantity a over r plus b over what?
Gamma minus r.
Yep. And so we're going to cross multiply. And we can rearrange this. So if you look at what you have on the r side, is you have r times b minus a, right? And then you have a gamma. And that is equal to 1 over r times gamma minus r, right? So what we get as a result is the equations b minus a equals 0 because there's no r here. So a equals b. And also a gamma is equal to 1, right? So what is a? A is what?
1 over gamma.
Right. And then from this equation, we have that b is
Also 1 over gamma.
because rearranging, we get 1 over that a equals b. So good. And now just to isolate this from my work, I'm going to put a box around it because that makes it a bit more legible. And then I use the star trick so that I can recover my sequence of equalities and continue it after this interruption. And so what I've done is I now know that this expression, it's equal to 1 over gamma. That's going to be a common multiple of 1 over r plus 1 over gamma minus r. And then this is an integral with respect to dr. And then the result is going to be 1 over gamma. And then, okay, so what are the two integrals respectively?
The natural logarithm of r and also the natural, I guess, minus the natural logarithm of gamma minus r.
So what happens is, notice this isn't r minus gamma, it's gamma minus r. So technically you can sort of do chain rule and then substitute minus r, but that introduces a negative sign with respect to dr. So it's going to be minus, or you can alternatively write this as minus r minus gamma, right? And you know how to integrate r minus gamma. So that's probably the easier way than doing the substitution needlessly. But we're going to get minus log gamma minus r. And then at this point, the constants, we're going to put a 1 over gamma there, right? Because we'd like to get rid of that 1 over gamma when we multiply through. And then the constant is in general going to be of what form? What do we want?
I guess log c.
That looks reasonable because we have logarithms. So let's just remember what we have. We have that kt is equal to 1 over gamma times this expression. So in other words, bringing the gamma over, we have k gamma t is equal to, and then we can just combine all of these logarithms together. So it's going to be the logarithm of c times r divided by gamma minus r. Sure. And then as a result, I get that c times r divided by gamma minus r is equal to e to the k gamma t. And then I want to solve for r as a function of t, right? Because I want to know what the population is as a function of t. So what I get is that CR is equal to gamma e to the k gamma t minus r e to the k gamma t. And now I'm going to isolate r on one side so that I can solve for it. So I get c plus e to the k gamma t times r is equal to, why is there, yeah, gamma e to the k gamma t, that's why. And now I can divide this over. So I get that R is equal to gamma e to the k gamma t divided by c plus e to the k gamma t. However, there's e to the k gamma t in both at the top and the bottom, right? And I can simplify this a bit. I can divide both top and bottom by e to the k gamma t. So as a result, I get gamma divided by, and then this will just become 1, and I'll rearrange them because I don't know why I'm rearranging them, but e to the minus k gamma t, right? So in general, this is what the function is going to look like, and this is sort of interoperates between two exponential regimes in the picture that I showed you. So it actually would be really cool if I also learned how to plot the function. Maybe I could write this function as a formula and then plot it alongside this, and then you'd see that it actually gives the curves that we want, right? That would have been nice. Okay, now I have 20 minutes left, and I'm going to describe a pretty cool thing. So I guess I have enough time to exactly talk about one topic. So this is all the examples that I'm going to do for now of separable differential equations, right? So separable differential equations in summary, so as a summary of what we did after our integration section, is that we said in general, an ordinary differential equation is going to be some function that involves x, y, and the derivatives of y, right? And so they can be terrible messes like this that are probably impossible to solve. But then you can also consider equations of the form dy dx is equal to f of xy. And this is sort of a generalization of the integration problem where there's just no y dependence and it's dy dx equals f of x. And sort of in that case, if you've looked at all of the slopes that you have on this line, they'd be the same slope because it can't depend on y, it can only depend on x. But here we're allowing dependence on both x and y. And the geometric significance is, like I've already spent more than an hour doing, is that you're trying to find a curve such that the specified tangents at each point are exactly what you have here. And this is called a direction field or a one distribution. And then in general, it's not like we can always solve this problem analytically giving a nice formula for it. But we're going to talk about later that there are existence theorems that do let you solve this problem in the general case. And numerically. So there exist numeric solutions, but they aren't necessarily represented by a formula. However, there are some classes which are nice and you can make progress. And one of them is separable differential equations, which is when the function fxy is just a product of a function of x and y. And how you solve that is you separate them onto both sides and then you integrate each side, right? And then you just add a constant. And the constant in general, you're not just going to write plus c, you're going to write some function of c that's going to be nice, and that's going to give you a nice family of solutions. Okay, now I'm going to consider a different family of solutions. And in general, I'm going to consider what are called linear ODEs. And this is going to be, actually, I'm going to expand to higher ordered differential equations as well. So a linear ODE of order n is an equation of the form and so what it's going to be is we're going to have some function, let's say, of x, and these are going to be denoted by subscripts. So in general, I'm going to have n+1 functions from n to 0. So this is going to be some function of x times the nth derivative of y. And then we're going to have these until we get to the first derivative of y. And then we're also going to have the 0th derivative of y. And what this is going to equal is some function of x. And this is called homogeneous if G is equal to 0. So in particular, what does this mean? I can't have y squared or y prime, right? Because here it's just y. This is the nth derivative, right? But I don't have powers of y. I just have the nth derivative of y plus the n plus first derivative of y all the way down to y multiplied by some functions of x, right? So I don't have expressions like this. So something like what we saw before, which would be something like y squared e to the x plus y prime plus sine x is not linear. But something like e to the x, the second derivative of y, plus sine x times the first derivative of y, plus, let's say, 2y. And then we can put any function of x here. So arctan is linear. Does that make sense? Now, in this case, would this equation be homogeneous or not homogeneous?
I guess it wouldn't.
It wouldn't. It wouldn't be homogeneous because it's after you have all of the derivatives of y, the sort of function of x that's not associated with a derivative of y, that's not the 0 function, right? I have a function here. So this is not a homogeneous equation. Okay, so what's the main point about linear systems? Sorry, not systems, about linear ODEs. So suppose that we're considering this equation right here, and I'm going to call this equation star. So suppose, let's say a function y subscript I is a solution of star. And that's why, okay. I guess I actually do want to write them down. So suppose y is a solution of star. So Fn, I'm not going to write the x, I'll just write dot y to the nth derivative of y sub I plus dot 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 plus f0 dot y I is equal to g of x. And suppose that we have a solution of the homogeneous equation. So I'm going to put a 0 here. And this solution is going to be YH. Right? So what's one thing that I can do with these two equations now that I've written them on top of each other?
Subtract them.
I was going to add them, but sure, it's either or. So let's add them. And notice that when I add them, I can group these terms, right? So I get Fn by yi n plus yh n, right? And then here I'll just get g of x. So thus, I can add any solution to the homogeneous problem to a particular solution of the inhomogeneous problem, and I'll still get a solution.
That's like a lot like in linear algebra.
That's why it's called a linear equation. So in general, I'm going to tell you what the punchline is. If you've studied linear algebra, then the set of solutions to the inhomogeneous equation will be a vector space. And the solutions to the inhomogeneous equation will be a vector space, but it will be translated to not pass through the origin. And so that's called an affine space. And I'm going to explain what this means in a second. But for the homogeneous equation, you can also see, suppose you have two solutions to the homogeneous equation, right? If you add those together, do you still get a solution to the homogeneous equation? Exactly. And then if you multiply a solution by some number, is it still a solution of the inhomogeneous equation? Right, because you can just put the number inside of here and it's still 0. So in other words, the structure of the solutions to the inhomogeneous equation is that you can scale them by any number and you can add any two solutions together. And what that exactly says is that you have a vector space structure on those solutions. Although if you studied linear algebra, you haven't heard that word. What does it mean? It means exactly what I said. You can add solutions together, you can scale solutions, right? And then if you have a particular solution of the inhomogeneous equation, in general, you're going to get an affine space of that particular solution plus any solution of the homogeneous equation. So that's what the solutions look like. Okay, that was me talking very excitedly about that, and I should slow down and actually explain this in more detail. So what I'm saying is that I can add any solution of the homogeneous problem to I'm going to say a particular solution of the inhomogeneous problem. Okay, homogeneous is the correct pronunciation, but I used to say homogeneous, and that's sort of wrong, so I might alternate between them, but for the sake of clarity, it's homogeneous. That's the actual correct word. And this will still be the solution. Also, I can add and scale solutions of the homogeneous problem. Sorry, of the homogeneous problem. Homogeneous. And so this is why it's called, the connection to linear algebra is why it's called a linear differential equation, because there is going to be a linear, or more generally an affine structure to the space of solutions to these problems. And let's see, we have 10 minutes left. So I guess I might end 5 minutes early, but I'm going to, and then I'll give questions. So what we're going to start studying next class is first order linear differential equations. So in particular, oh, I guess I can say one thing about it. I guess I can use all 10 minutes. In particular, first order linear ODEs are equations of the form and so it's going to be, let's say, f of x times y prime plus g of x times y is equal to h of x. I thought this would be enough, but I guess I'll just do 1,000 more. Now dividing by y, or with equal generality, we can just divide by f of x, ignoring division by 0, and then we won't have f of x. Or in equal generality, y prime is equal to, let's say, plus f of x y is equal to g of x. So I've just divided by f of x, and I'm going to say that this is as general because forget about division by 0, right? Now, okay, so if you actually look at this, this is a first order equation with y on one side. So it actually is an equation of the form that we were considering for most of today. In particular, y prime is a function of x and y, right? So this implies that y prime is equal to f of x, y, I guess minus f of x, y plus g of x. So it's actually not like the fully general expression of x and y, but there are some expressions of x and y of this form. And in that case, where it actually corresponds to a linear equation. And we know a bit about the solution space structure. And as I'm going to show you, there's actually a general form for solving all first order linear differential equations, assuming that the integrals work out. Or if you can write it in terms of integrals, you can write a general solution to these. So what am I going to say today? Today, I'm actually going to give you an example of what about the homogeneous case. Right? So let's do the homogeneous case. We can solve this pretty generally. So this is y prime plus f of x, y is equal to 0, right? And what kind of equation is this?
First order homogeneous.
Yes, but also what
Mhm.
type of equations were we discussing immediately before this?
So one distribution.
That's the general problem of first order equations where you have this. I'm thinking about separable equations. This is separable, right? Because this says that dy dx is equal to negative f of x times y. And that's a product of a function of x with a function of y, right? So it's a separable equation. Let me just also, it's getting darker. Open the blinds. So if we do this, what we're going to do is it's a separable equation. So cool. So we get that dy over y is equal to negative f of x dx, right? And so as a result, I think I don't even need more space than this. I'll get that the logarithm of y is equal to negative the integral of f of x dx. And then you know what? Let's just insert a constant here, although the integral will have a constant. Let's say I insert a constant. And why not make that constant log c? That looks like a sensible decision. And so what we get is that y is equal to c times e to the negative integral of f of x dx. So in particular, what we have is that if we have a first order linear homogeneous equation, then it's in particular just a separable equation. And if you can integrate f, then you can solve the equation, right? And so what we're going to see at the start of next lecture is that in fact, there are going to be two methods. One of them is going to be called, well, actually, one is going to be called the method of integrating factors, and the other one is going to be called the method of variation. And there are going to be two methods that work equally well to solve the general first order linear equation. And then both of these methods are going to generalize to different higher order methods for solving different equations. So that's going to be cool. So hopefully this was a fun first lecture. I didn't realize, I think I got really excited about the plots. So I had not like literally practiced this lecture, and it turns out that looking at the plots is actually pretty exciting. So hopefully you got some of that excitement as well. And so, yes, I will recap this lesson about linear equations, about having a linear space of solutions or an affine space of solutions. And then I'll recap this at the beginning, and then we'll learn how to solve these equations in general. Sounds good? Oh, and then if you have any questions, you should email me. And also I need to tell you one more thing. So on the syllabus, I wrote that I'd have 5 assignments, but I don't have the first assignment ready. So you know what, you're lucky. I'm going to make it 4 assignments. I'm going to post the first assignment by midnight on Friday, and it'll be due next Friday. Sounds good? Okay. And so my email is astra.kolomatskaya@gmail.com, and that's on the syllabus. And I've sent all of you the syllabus. Someone just registered for the course, so they haven't received that email. So you know what? I'll create a website, and then I'll put the syllabus on it, and probably I'll do that tomorrow or maybe Friday morning. And then I'll also put the assignments on it, and then I'll send it out again. But actually these notes, it would be good to send them out. So you know what, for the moment, I'm going to send you a PDF of these notes, and then I'm going to set up the websites, and then I'm also going to put the syllabus on that. Cool. Okay, and the next lecture is tomorrow at 6 p.m. And then it's Mondays, Wednesdays, Thursdays, 6 to 9.
Quick question. I noticed that
Yep.
it's recording. Are you gonna post these recordings?
Yes, thank you. Great question. Excellent question. I'm going to send you the link on Zoom, and I'm also going to post them on YouTube.
Okay, thank
Although
you.
the YouTube uploads will take a while to process. They take like several hours to render a 3-hour video. So I forgot about the recordings. I will send you a link to the recording. It takes about an hour for Zoom to process the recording as well. So as soon as that's available, I'll send you a PDF of this as well as a link to the recording.
Thank you.
And thanks for asking that. And you reminded me about the recordings. Yes. Okay, any other questions?
Well, just to make sure, so there's 2 tests and 4 or 5 homework assignments?
So 4 homework assignments. They're going to be due on Fridays, with the first one posted on Friday, due a week from then. Then we're going to have a midterm, and I guess I should schedule that soon because some people like need to get time off from work. It's going to be a 24-hour midterm. So if you like have work, you should take a day off on the day of the midterm because it's a 24-hour take-home exam, and you actually need, a bunch of the waking hours to do that. And how the final is going to work is it's going to be an oral exam. And the reason that I'm doing an oral exam is because oral exams are just the most BS-proof way of learning how much you know. And if you sort of read the course syllabus, then in the last 2 courses that I taught, I actually gave a breakdown of how much each component is worth, but that was sort of a lie. And this time I wrote how I actually grade. How I grade is that I consider all of your work and I rank all of you individually. And then when I rank all of you, clear grade boundaries appear. So I want to know how good you are at problem solving relative to other people. And all of the work is just a way to tell me that. And again, I spend there are 14 people here. I'll spend like 4 or 5 hours thinking about this. So I am going to get to this is going to be a really good and objective ranking. So the oral exam is a very good indicator for that. And if you're worried about sort of oral exams being thinking on the spot, then don't worry as much, because I'm going to give you all of the problems to the oral exam a full day or maybe 2 days in advance. And then what you're going to do is you're going to do it like a written take-home exam. You're going to write up the solutions and you're going to post them online. By online, I mean on Blackboard. And then I'm going to take a look at them for a few minutes before the exam. And then I'll ask you questions to ensure that you understand what you wrote. And then I'll also ask you some extensions of the problems, or if you didn't solve a problem, I'll give you some hints. So there will be a tiny bit of me guiding you through a problem as well. But mainly it's going to be based off the work that you submitted, which you're going to have like a full day to think about. So it's not going to be as much like thinking on the spot. But the point is that if you copy answers from the internet, you're going to get screwed and I'm going to report you. So do not copy answers from the internet. On the final exam, and I'm going to just give like a 20-minute speech about this, it's that it is BS proof. If you do not understand what you wrote, that is going to be very evident and it's going to be very bad for you. So that's why I have a final oral final exam, because it's not about me assigning a number to something. It's about me getting a picture of how good you are at solving problems so that I can rank everyone. Now, does that say that the grades are 100% subjective and based on how I feel? Well, there's no such thing as an objective grading system. This is an argument that I do want to make and extend. So yeah. But it's a good grading system. What it means is that I'm going to hold you to a very high standard. And it turns out that being held to a high standard feels much better than being held to a low standard. If you have like being held to a low standard is a 500-person calculus section. It's completely soulless. If you like mess up an assignment, then you're not getting an A already. Or if you mess up the midterm. And you wouldn't have take-home midterms. It would be a 2-hour timed exam. Let's say you had a bad day. Let's say you did poorly on the midterm. Bam, you're not getting an A in the class. In this case, you mess up one of the components, whatever. If you're good at solving problems by the end of the course and you show me that you actually understand stuff, I'd have no problems giving you an A. So sort of the standards are going to be much higher and I'm going to expect more of you. But if you come anywhere close to meeting the standard, it's just like free A's. Okay, not exactly free A's, I shouldn't say that. But just show me that you've learned something substantial and then I'm going to be happy, right? That's the main point. Does that make sense? Any questions? So like, I think that when you're running an online class that has a small number of people, this is the correct system to use. And it deals with a lot of problems of cheating that come up. And it just makes, I think, the grades actually reflects whether you learned something or not. That's really the main point, because I do want to get you to engage with the course. I want you to be excited about the material and I want you to practice some of the problems. And if you do that, then I'm going to be happy, right? Okay, so I guess I did a amble about my post-amble about my grading system and how this course is going to work. And I wrote that the syllabus. And like the syllabus sounds a bit harsh, but at the end of the syllabus, I say that like really this grading system, it's more generous than a grading system like a soulless 500-person calculus class. It should be a better experience. If you're being held to a high standard, it feels better because I respect you and you should respect yourself. Okay, so that's the end of my rants. And so hopefully you have a good 21 hours until the start of the next lecture. Get some rest. And send me questions by email. Okay, have a nice day. Bye.
Cheers.